So here we're going to take a look at some examples and talk about how to organize our works to make it all very helpful for dissecting what are we looking for and how do we find it. So here's just a general guide for how we want to go about these. First off, defining variables and their units can be very helpful. Most of the time, we will have a time variable that's at work as well. So how things are changing per minute, per hour, things like that. Next piece is defining a relation equation. So how do we relate our variables together? And this is where, in general, we want two variables here. And if we have more than two variables, we might want to look for how we can relate certain variables together and make substitutions. And we'll talk about that when we get to our final example that we look at. Then our next step will be to use implicit differentiation, and this will give us a rate equation. So often when we do this, we're looking at taking the derivative with respect to t of both sides, and then simplifying where we can. And then we just use that and plug in what we can and simplify until we can answer the question which is being asked. And an important part is to always go back to what is the question being asked, because sometimes we might solve for pieces that we don't actually need. So I'll also talk about how to kind of keep that in mind as we're going through these questions. Okay, so first scenario here, we have a rocket is located 4 kilometers from a telescope, and it is launched straight into the air. And what I'm going to do is I'm going to get a picture going, and I'm going to just already apologize for my silly cartoons that I draw, but hopefully it'll get the point across. Okay, here is our rocket. And then we have the ground, and then we're going to have a telescope. All right. And we have the rocket where it launched to where the telescope is 4 kilometers. Okay. That takes care of the first sentence. At 3 p.m., the angle between the telescope and the ground is pi over 3. So also going to have a height to the rocket, and then also going to have this angle with the telescope. And they're telling us at 3 p.m., and actually, I'm just going to mark this angle right here because that angle is changing. So in fact, let's talk about this real quick. Things that are changing in this equation. We have an angle. We have a height. That 4 kilometers is stuck. That's staying the same. What's changing is this angle measurement and the height of the rocket. Also, this over here, but what we're going to find is they're not asking for that, but that is also changing. But that 4 kilometers is stuck. So with our picture, we could start thinking about what is staying the same, what's changing. So what I highlighted there is all the pieces that are changing. And what we're being given here is at 3 p.m., that angle is pi over 3 and is changing at a rate. So that angle is changing with respect to time at 0.7 radians per minute. Now those pieces of information are a little snapshot, just at one point in time, how things are stuck and how things are changing. So what I want to do is hold off on using any of those values for as long as I can in my equation. So there's my snapshot of things that are changing, but we're going to look at them at a moment in time. What is the rocket's velocity at that instant? So with all that information, we want to know, how is the height changing with respect to time? That would be our rocket's velocity. So we want to know what is dH dt? So that's going to be our question that we want to answer. Okay, so in terms of defining variables, so we have the height of the rocket, that's going to be in kilometers. We don't care about this x value. They never mentioned this distance between the rocket and the telescope, so we can ignore that. We have an angle measurement that's being given in radians, and then we have that 4 kilometers. Okay, so those are my variables, and I want to relate them together. And if I have this picture here, where I'm looking at an angle measurement and 2 side lengths, I'm thinking trigonometry, especially because it's a right triangle. We have a nice right angle right there. So I have an angle measurement, and then I have information about the opposite side length and the adjacent side length. So what I'm going to do is write a relationship in terms of tangent. So tangent of that angle measurement is equal to opposite, which is h, over adjacent, which is 4. And that's a nice, concise equation that relates all of our pieces that we're interested in together. And again, I'm keeping theta and h just in terms of the variables for as long as I can, because I don't want to plug in that 3 p.m. information yet. I want to have the only fixed value be that 4 kilometers, because that is the only value that's not changing as time is passing. Okay, so that sets up the relation equation. Now what I'm going to do is take the derivative with respect to time. Again, because I'm looking for dH dt. So I know I want to take that derivative with respect to time, because eventually I want to be solving for dH dt. Okay, derivative of tangent of theta. So we're going to have secant squared theta. Again, because our variables don't match up, we're taking the derivative with respect to time of something involving theta. Because of chain rule, we'll also have multiplying with d theta dt. And then equals the derivative, and you could even think of the 1/4 as separate here. So derivative with respect to t of h would be dh dt. So we've taken the derivative. We don't really need to simplify anything. What we could do is, now that we've taken the derivative, we can plug in values. So what we know is, we know our angle measurement, we know d theta dt based on the information. So we're going to be taking secant squared of our angle measurement of pi over 3, and then that's going to be multiplying with d theta dt, which they told us is 0.7 radians per minute. And when I go to plug in, I just double check positive versus negative, and this angle is in fact growing. As the rocket goes up, that angle is going to get more and more, so that is a positive 0.7. Equals 1/4 dH dt. And what we want to solve for is dH dt. So I'm going to move things around. In fact, I'm going to go ahead and multiply both sides by 4 to get that away. So we have 4 times secant squared of pi over 3 times a 0.7. And we could go ahead and plug this into a calculator, but let's just, for some good trig review, find that exact value for secant squared of pi over 3, because that could be handy. So pi over 3 is up here, and it goes with the coordinate. Let's see, small coordinate for x, so that's our 1/2. Large coordinate would be the root 3 over 2. And with secant squared, so secant squared of pi over 3 is the same as 1 over cosine squared of pi over 3, which is 1 over 1/2 squared, which will be 1 over 1/4, which is 4. So we can make this substitution of, we have this 4 out front, and then where we have secant squared of pi over 3, that's the same thing as 4, and then times a 0.7 equals dh dt. So let's see, 2.8 times 4, so 11.2. Okay, so when, or let's say at 3 p.m., all that information follows. At 3 p.m., the velocity of the rocket was, or is, 11.2 kilometers per minute. Okay, so just a walkthrough. They give us some information that's fixed. They tell us about this moment in time. So 3 p.m. had this angle, also had this rate of change. So we put that off to the side and save it for later. And we want to know what is the rocket's velocity at that instant. So we know what we're trying to find. So create a relationship between the variables, making sure you're not plugging in things that are coming from that snapshot in time. Take the derivative, follow the rules, and then after taking the derivative, we can plug in the values and simplify and solve. And then when we get there, make sure we're actually answering the question that was asked and put it together in a nice sentence. All right, 2 more examples that we're going to go through here. And this might be kind of a big video, so feel free to pause and return to it as needed, or try these out. Even just trying to define the variables and get a picture going is such good practice with these. Okay, we have an airplane is flying at an altitude of 6 miles toward a radar tracking station at a speed of 500 miles per hour. When the distance between the plane and the radar station is 10 miles, at what rate is the distance decreasing? And just to see, when the distance between the plane and the radar is 10 miles, so they're saying when, this I'm seeing as that kind of snapshot moment in time. So that's the piece I want to save for later. So let's get a picture going. We're going to have the ground. We're going to have an airplane. Something like that. And radar. So we have the plane is flying at an altitude of 6 miles. So let's go ahead and go with this altitude is 6 miles, and that is stuck. It's staying at 6 miles there. And the plane is flying towards the radar and going towards there, that rate of change. Ooh, let's hold off there. And then we're talking about the distance between the plane and the radar station. Here's a nice right triangle coming through. They don't mention anything about angles like in the last example, so this has me thinking we're just working with the outside of this triangle. So things that are changing, this distance, or rather this horizontal distance between the plane and the radar is shrinking. And then also this distance between the plane and radar in that diagonal form, let's call that y, that's also changing. So those are my changing pieces. But that 6 miles is stuck. So what we're interested in, and x would be in miles, y would also be in miles. So we have our units. Then we have information about how x is changing. We know dx dt, this is our velocity of the plane, is 500 miles per hour. Also, what we need to keep in mind is x is shrinking, so that's decreasing. So what we need to do is make sure that we express that as a negative. So because x as a distance is getting smaller, that dx dt needs to be negative. Okay, so this little snapshot in time that we're looking at, it says when the distance between the plane and the radar station is 10 miles. So that's telling us what y is. So that's going to be part of our moment in time. And we want to know at what rate is this distance decreasing. So we want to know what is dy dt. That is our question. Okay, so with that, I'm looking at relating these three pieces together. I have this fixed value, a side length, another side length. We have an x-right triangle, so we're going to do Pythagorean theorem. So we're going to have x squared plus 6 squared equals y squared. And from there, let's take the derivative. So let's see, we're taking the derivative with respect to t. So taking the derivative of x squared, we'll have 2x, but then with chain rule, we will also have dx dt. Derivative of 36 is just 0, equals derivative with respect to t of y squared, we'll have 2y, and then with chain rule, we'll have dy dt multiplying on. So we've taken the derivative, so now we have this rate equation, and now we can plug in things that we know. So this moment in time, we know this distance is 10 right here. We know dx dt as well, and if we needed x, we could solve for it. So let's see, x would be equal to, so x squared plus 6 squared is 10 squared, so this is going to come from the square root of 100 minus 36 with our Pythagorean theorem, which will give us an 8. Okay, so at this moment in time, we would have 2 times 8 times negative 500 equals 2 times 10 times dy dt. And let's see, that would be a negative 800,000. 8,000 equals 20 dy dt, which means dy dt would be negative 400. Okay, so putting that together in a sentence is when the distance between the plane and the radar station, so setting our moment in time, is 10 miles. That distance is decreasing because it's negative by 400 miles per hour. So it's that distance between the plane and the radar that's shrinking as well, and it would be at a rate of 400 miles per hour. Okay, let's go on to our last one here. So we have a water tank, has the shape of an inverted cone. So what that would look like is we'd have the top, and then sides, like that. So there's our inverted cone. The height of the tank is 10 meters. So a height of 10 meters, and the radius at the top of the cone is 4 meters. That should say water is pouring into the tank, not what is pouring. We know what is. Water is pouring into the tank at a rate of 6 meters cubed per minute. So we have a faucet of some sort, and water is going into the tank so that we have a water level of some sort. So we have water in the tank, and we know that it is coming through at 6 meters cubed per minute, and that's gonna hold steady right there. So let's go ahead and write that down. So that would be for our volume of water, that volume in relation to time is increasing at 6 meters cubed per minute. So what we want to know is how fast is the water level rising at the instant the water level is 5 meters. So if we go to the water level, there's some radius and there's some height. So we have a height and a radius, and those two things are changing. And that height is increasing, and so is the radius, but we're really just talking about the height of the water. And what we want to know is, how is that height changing in relation to time? That's what we want to find. And they want to find this when the water level is 5 meters. So that's our moment in time that we want to save for later. So having that height of 5 meters is going to come through later on. Okay, so we're working with the volume of a cone here, and we're thinking about the water level. That's what we're focused on here, is just the water level. So we have, for a cone, the volume is 1/3 pi r squared times h. Now, if I take the derivative with respect to time here, let's even write that. We can do that, but something that's going to come up is this radius, and having dr dt be part of this, like how the radius is changing with respect to time, it's too much information, or not even too much information. It's too many variables. We're really just interested in how height is working along with volume. The radius is just kind of extra. So this is a scenario where we have too many variables. So what we want to do is simplify this so that we can express this volume only in terms of h. So we want to make an adjustment so that this is only in terms of h. We could also change this so that it's only in terms of r, and when I would do that is if the question was asking about how the radius was changing with respect to time. If that was our goal at the end, then I would do dr dt, and I would adjust h to be in terms of r. However, with this, we want dh dt is our goal. So with that, I want to replace r right here with something in terms of h. So let's go back to our picture and see how we can do that. Something we have going on here is the idea of similar triangles. So this might be a little bit of geometry review here. So what I'm visualizing here are two right triangles in this image right here. So let me bring that to the side here. So it's kind of like I'm separating up my cone and turning it two-dimensional in terms of two right triangles. First one being the 4 meters from the radius and the 10 meters from the height. But then we have the second one formed from the water level, and that one we're looking at a certain radius and a certain height. So similar triangles are two triangles that have the same angle measurements. All three of them have to be the same. So both have right angles. This angle would be the same as this one by corresponding angles, and then they share that angle, so all three are the same. And when we have that, we can make ratios of side lengths. So how 4 compares to R is going to be the same as how 10 compares to H. So I can make these ratios as 4 to R is equal to 10 to H. And with a little cross multiplication, 4H is equal to 10R. And because I want to replace R in my equation up above, I'm going to solve for R by dividing by 10. So R is equal to 2/5 H. So end up with this relationship, and that's where that overall height and radius from our total inverted cone comes into play. So now we're going to make a substitution. Going back up here, I'm going to say V is equal to 1/3 pi, and then where I have R, I'm going to replace that with 2/5 H, and that's being squared times H. And I'll just do a little simplifying of 1/3 pi, and that would be 4/25 H squared times H. And then just one more step of simplifying. Let's see, 4/75 pi H cubed. Okay, this is better because now I just have volume and H, and that's a good amount of variables to work with. So now I'm going to go through and take the derivative with respect to time. So on the left-hand side, we'll have dv dt equals that 4/75 times pi, and then h cubed will turn into 3h squared. So let's see, 3 times 4 is 12, so I'm just going to change that numerator to a 12 there, and then h squared, and then because of chain rule, we'll also have dh dt. Okay, so now I want to go back and see what can I plug in. So again, we had that dv dt is growing, so it's positive 6 meters cubed per minute. We're also looking at the moment that the water level height is 5 meters. So let's plug those in. So we're going to have 6 equals 12/75 pi 5 squared dh dt. Which, let's see, that would be a 6 equals 25 divided by 75, which would be a 1/4. So 12 divided by 4. Ooh, I'm moving a little too fast there. Let's see, 12 times. I think we're good, but just to make sure. Sorry, a 1/3, which leave us with a 4. Yeah, okay. See, move too fast and I'll make calculations too quickly. So that'll be 12 divided by 3, which is 4. So for an exact answer, dh dt would be 6 divided by 4 pi, or 3/2 pi, which is about 0.4774. And then height would be in meters, and then time is passing in minutes. So when the water level is 5 meters, the height is increasing by 0.4774 meters per minute. And there we go. Okay, someone had some extra steps because we needed to adjust our variables, which can happen sometimes. So we got our picture, put in the things that are fixed, save things that are kind of changing for later. And then once we come up with our formula, if you have too many variables, think of a way of relating those variables together so that you can make a substitution, take the derivative, plug in those things from our snapshot in time, and simplify, and then write a nice sentence answer. Okay, that was a big video. I don't like going to 30 minutes, but hopefully those will help you answer some of the related rates questions.